This is something that has been sort of fiddling around in my head for a little while, and it's not necessarily novel, but when I see two things come together, I like to write up a talk, and it just helps me sort of ground things a bit. And then I gave this to some friends at work, and they said, "Oh yeah, I thought that was interesting," so I thought, "Great, let's share it more." So it's just really combining two sort of things that I certainly have used a lot, and I just love these ideas that sometimes when you get combinations of things and you just sort of look at them the right way, they're the same thing, and you're like, aha. So I love those aha moments, and I'm always looking for more of them. And this one, I guess, talks about cross entropy and metric learning. So there's kind of 6 parts to this talk. What is both of those things? That's sort of, we've got to have some grounding in what these two things are. So I'll start with cross entropy, and then I'll go on to metric learning. And then I'll sort of want to go through some combinations that align a little bit with the ways that I've used metric learning in terms of the sort of techniques. So things like triplet loss and M-pairs loss, and the simpler forms of what we're sort of trying to do with metric learning, and then sort of they fail in interesting ways, and so I'll talk about those. And then sort of segue just a very little bit of geometry, which is one of the things that we're going to use to tie these together. And then we've all tied them together. So we'll talk about how we can use this thing from the start, which at first glance doesn't seem to anything to do with something that you'd want to use for metric learning. But I love it when you square peg, round hole, smash them together. And the last one, I just wanted to sort of talk about a couple of interesting results, papers that I've sort of seen that have been using this and again over time. And I think I didn't really click with me what people were doing with it from a long time ago. So it might not, a lot of this might not be news to people, which is cool. But it was sort of news to me, the way that this interpretation. So it's really interesting. Okay, so cross entropy. Let's start with that. So say I'm trying to do prediction, and I'm trying to do like 3-way classification. So I want to have a model that outputs 3 probabilities in a distribution. So class 0, 1, 2. And so far, my awesome neural network has got down to the point of having sort of 4 outputs at some stage, and that there's some values coming through these activations. And I want to say, well, I've got 4 things and I want to make them probabilities. What am I going to do? Well, the first thing we do is like a dimensionality reduction. So I'll drop it down to like a dense layer that's got like three values. So I get the cardinality right, at least. And then depending on what the activation of this thing is, if I've got no activation and we're just talking about the activations from before times by weight matrix and a bias, I'm going to get some range of values, and those range of values is unbounded. Yeah, this can just be whatever they'll be plus, they'll be minus, they'll be all over the place. So they're not really probabilities. So we need to normalize them. And the standard way of doing that is with a thing called a softmax. So softmax, we're going to take e to the power of each of these values, and then we're just going to divide them by the sum. Classic normalization. And that normalization is great because it does 2 things. It makes sure that all the values are between 0 and 1, and it makes sure that they sum up to 1. So it's definitely interpretable as a probability distribution. And so now I've got what I wanted. I've got these 3 things that sort of look enough like probabilities that I can use them as such. And there's a couple of names we use of things. There's these softmax values that come when we apply that softmax function. And then there's the ones before called the logits. And, honestly, I don't know why they're called logits. Probably some weird thing from like 100 years ago. But we need to keep that name around because we're going to use it. But the main thing is that we've got this method of taking what otherwise would be sort of probabilities and making them look like probabilities. Cool. So that's step 1. We needed a way to make things look like probabilities. Now we need to train. How do we sort of have an objective we train against? And that's where cross entropy comes in. So cross entropy is a measure of distances between probability distributions. And that's what we want to do when we make a loss function. So here's a couple of examples, and I'll talk through them. If I had my y true being, it's the first class, and then my output was something like this, where I was getting 98% for that sort of class, then I'd want this loss to be low. And let's look how that cross entropy does that. It's a pretty simple function. We're just going to log the predicted value. And so, as this approaches, this is going to be a negative number because remember probability is 0 to 1. And as we approach 1, the log of that will tend to 0. So this will, as we want with a loss, as we get closer to the real thing. And what's interesting about this is that we take the log of the predicted value and we actually multiply it by the true value. And I remember when I first saw this, I thought, oh, that's really weird because there's only one true value here. There's only one in the true. So this is acting like an indicator function for the one where we're making the prediction. And the very first time I saw this, I remember way back when I saw this, I went, well, that's weird because the other ones that aren't true, they're going to be zeroed out in this loss. That does make sense. But then I came, hang on, you've got normalization. So when you're taking this value and you want it to be high as part of that normalization, one way to do that is to make the other ones low. So not only do you want that number to be high, but you want it to be high relative to the others. So even though that sort of zeroes out the loss for the ones that aren't zero, the best way still to get that to be high is to make the others low, because that's how you normalize. The lower these other ones are, the higher that one becomes. And then because all these things are negative of that log, because we're less than 1, we just negate it at the end. So that's no big deal. So it's very, very standard sort of thing. But what's interesting, if we look at the second one, where we had a true value in the first one, this would be a case, if you look at it, where the loss would be high, because we're predicting the last class, but the true value was the first class. So I'd want that to be high. But here's the interesting aha moment. If you look at this, if we're predicting 0 in that case where the true one was, we're asking for log of 0, and that's trouble. So there's some numerical stability we need to be careful about, because log of 0 is going to cause us grief. So under the hood, when we're actually using this sort of loss function, we often don't use cross entropy directly in this form. Instead, what we use is we use a version of it, cross entropy, where we don't pass the softmax values, we pass the logits. So, and this actually happens under the hood. Something like Keras will do this for you. You'll have an activation like a softmax, and that's what you use for prediction, like if you're actually using it for inference. But when we come to calculating loss, we won't actually apply that softmax. We'll just use this function. And you can do this because you can just, this formula here, you can just rewrite it. If you know that y predicted is e to the x over the sum, like the normalization, you just sort of shift e's and logs around until they sort of disappear, I guess. So you can sort of do these tricks with math if you know what the y predicted is. So we do that for numerical stability. That's one of the big reasons. And so frameworks will provide us this sort of thing under the hood, that if you're doing softmax cross entropy, you can use with logits. And so we just pass the logits directly. And this is sort of the same as what I just had in the last slide. The label here being the second one, the way you get the loss being low in that case is you make that one high, and you make the other ones low. Because that's, again, if you go all the way back to this normalization, that's how you do it. To make that value high, we make the logit high, and to make the other ones relatively low, we make them low and negative. So that's the forcing function that the training will do. And if we look at the second one here, if I had a label of 1, but I was sort of predicting, you can see here, what's the one that's the highest, the argmax, this one, I'll be predicting this value, I'd get a high loss function. Okay, cool. So that's one thing I want to make reference to in the toolbox, the softmax cross entropy with logits. Secondly, and this is less important, but it'll come back. Because the y true is 1 hot, we actually just have 1 and lots of zeros. We can use this other one, which is a sparse version of it. So this is a great name, isn't it? Sparse softmax cross entropy with logits. Man, that's something to write to your grandmother about, isn't it? So this idea here is we don't pass zeros and ones, we just pass what's the index of the one that is 1. So the label becomes just a numerical value, which is 1 in this case, which is the 1th element. So that would be a good case. And in this case, we're saying the label is 0. That means the 0th element, but we predict the first element, so the loss is high. So there's another thing that we have available to us, the sparse softmax cross entropy with logits. I love it. And last thing, we just got to remember, everything's batched. Everything we do in these sort of systems is batched. So we may have 4 values where we run through it at once. So the 4 values here in these labels are the 4 instances, and each instance has 3 values. And sort of what this one does is just each independently just gets run basically. So and this loss will give us the array of the 4 values. And just to get a scalar loss, we just normally average them, or maybe they're weighted by like an instance weight or something, or a class weight. But you know, the main point is that they've got batching. So this function will take a matrix here, where it's got some number of rows, they're each instances, it's got some number of classes, that's the distribution, and then we've got some labels. So why do we batch? Well, you know, I guess mainly it's around the idea that we get a lot of speed up. There's a lot of you know, hardware. When you're doing matrix vector multipliers, you can do some tricks under the hood. So there's a big reason to make things batch. There's also lots of reasons theoretically around gradient variance and stuff. When you do an update over a bunch at once, you can sort of do this trade-off between single instance versus full batch. So sort of in between. So that's the main thing. I just want to say that there's this function available to us that does this sort of stuff. And again, the idea that the labels here, because they're the indexes of what we want to get, and the interpretation of these being values before a softmax, this as it's represented will say, I want the network to learn to make all the values low, negative, except for the one that you've told me about, so the 1th instance, and I want to make that high. That's the sort of pressure that this function, as a loss function, puts on the network during training. Okay, so let's just park that, and well, let's try to remember that cross entropy with logits, that's the motivation, makes the label element large, positive, and the best way to do that with the softmax is to make the other elements large negative values. Okay, cool. So that seems kind of nothing to do with metric learning, but let's just park that. That's why it's interesting. So let's switch to metric learning. So what is metric learning? Well, it's a pretty broad field, and I don't have a good definition of it. But for me, it's about learning distances and about learning sort of primarily. I've been using it for learning embedding models. So we've got some model, and we give it some x, and there's some. Normally we're trying to do like a prediction or something, but there's a lot of motivation to build models that do embedding. So we take an x, some interesting interest, and we embed it in space. And metric learning is often about the idea that for some set of x's that are similar by some definition of similar, we want them to be close by some definition of close in the embedding space. And there's lots of reasons to do that, because it's lots of reasons for, in terms of like nearest neighbor sort of calculation, where you might say, I've got some images which are hard to compare, but if I can sort of do this training that sort of puts them in this embedding space, and then it turns into like distance calculation, that's really fast. So we often do this as a form of dimensionality reduction. It's often a first step in a lot of examples of things like, word to vector example is an example of this. Like we have a model that translates from text into embeddings, because once you've got embeddings, once you've got floats, oh man, they go everywhere. Like you might have trouble bolting your arbitrary text and image into a network, but you'll never have a problem just concatenating a vector. So there's a lot of reason to do these types of models. They become building blocks for other things. So metric learning for me has been mainly around this idea of how do you train these models. And what's interesting is that often with supervised learning, we will say, I hereby declare I want you to train by giving you the following pairs of inputs and outputs. So here's an X, and I want you to go to this Y. And here's another X, and please go to this other Y. And often we frame things a little bit different in metric learning. In the metric learning case, when we were trying to learn embeddings, we don't necessarily always care where the embeddings are. There are reasons to want to sometimes, but we often don't care where you embed. What we instead care about is, for particular sets of X's, I want some constraints to hold. Like maybe I want these X's close and I want these other X's far away. What the actual embeddings are, who cares? Like just put it wherever you like. But I have some constraint over sets of X's, and that's often a little bit framing different. So the first version I saw of this is this approach called triplet loss. And so let's go through that, and particularly because it has an interesting flaw that meant other people wanted to do more complicated versions of things. So what is triplet loss? Well, triplet loss is this idea, very abstract, quite broad, where we're going to, again, talk about the training not in terms of X and Y pairs, but in terms of triples of inputs. And they commonly have these names, anchors, positives, and negatives. And often the anchor and the positive, if we're thinking about this purely from a supervised sort of view of things, then we might say the anchor is some chosen instance, and the positive is another instance, but the positive and the anchor have the same class. So they're like, if this was a truck, if I randomly pick like from some images and I've got a truck, I might pick another truck, and that would be my positive. So it's positive because it's the same class. And then we're going to have another instance that we call the negative. And the negative is another instance somewhere where it's not the same class. And the idea of triplet loss is to say, given this triple of an anchor and a positive and negative, I don't care where you put them. I just want the positive to be closer to the anchor than the negative. Because if that idea held for all combinations of all anchors, positive and negatives, you'd have this awesome embedding space. You'd have all the ones of one class sort of next to each other because they're all happy friends because they're anchor positives for each other. And they're all far away from all the negatives. So what's really interesting about this is because we don't necessarily care where, we just care about the constraint. And so how do we specify that constraint? Well, it's the simple version of triplet loss is really elegant. I think it's really beautiful in terms of what a loss function means. So what I care about is this idea of this distance between things, yeah? I've got an anchor and a positive, and I want the distance between them to be less than the anchor negative. And again, I don't care where, I just care about the distance. So I can rewrite this a little bit. And I'll go through this pretty rapidly because it's not the main theme of the talk, but I can rewrite this to move this anchor negative onto the other side. And then I'm basically getting a comparison to 0. And then what I can do is I can say, I'm going to actually treat that value, this difference between them, as a loss function clipped with 0. And I'll draw a little picture here, and I'll go through an example. So if the positive is really close to the anchor, this value will be small. And if the negative is really far away, this value will be big. So a small number minus a big number is a negative number. And if I max that with 0, I get 0. So I know I said that very rapidly, but I'm basically saying this is the area where if I think about this x and y distance, x as being the difference between these two, over this area is when the positive is closer than the negative. And what I'm going to do is I'm going to clip that and say 0 loss, 0, because that's what I wanted, wasn't it? I wanted the positive to be closer to the anchor than the negative. But say the positive is really far away. The anchor minus the positive is a large distance. And if the negative is closer, then this large minus a small number is positive. And that's this area here. And what I'm going to do is I'm going to actually say, just take that distance, take that difference in the distance, and just use that as the loss function, as the loss value. So over here, we've got this value where as the positive gets further and further away from the anchor, over past the negative, the loss goes up. And this is beautiful, isn't it? Because what is a loss function? It's something that 0 means you're doing well, and anything positive means that you're sort of doing worse. And so why not just use the distance as the loss? It's kind of wacky, but it works. And so this is a fundamental idea, though. This idea of this difference and the clip. This is called hinge loss, and I leave it to an exercise to the reader to determine why they call this hinge loss. It's pretty cool. So someone had fun back in the 40s or something when they invented this in terms of naming, at least. So fundamentally, there's this idea of representing distances and differences in distances and using a loss. Now, the big problem with triplet loss is as you're training this and you've got this idea of this regime over here where the loss is 0, as soon as the positive is a little bit closer than the negative, you get no training. Loss equals 0, bang, everything stops. And so depending on how you're selecting these anchors and positive and sort of negative combinations, you can get into you can very quickly get into a case where your training just slows down to nothing. And as you're sampling all these instances, you get to this element of what's effectively like converging, because the negatives you've been choosing randomly turn out to be too easy to get. So there's a whole class of approaches that deal with this to say, well, let's try to find hard negatives. Let's try to find the ones that actually are really close. And so people do this as offline jobs or selectively within batches or whatever. So there's all sorts of tricks. But this is the biggest thing that I've always seen from triple loss. Very quickly, we get to this point where the positives are just good enough. And there's other things you can do, like you can stick a margin in there. You can stick an artificial little delta in here, basically, to say the positive has to be closer than the negative by a little bit, and you can you can anneal that even if you want. But those are sort of add-ons. Now, one thing that is when I first using triple loss for a long time, and then I saw this thing called N pairs. It capitalized on some really important part of how we train. And so let's talk about N pairs. So here's an example that I've chosen for training triple loss. It's got an anchor and a positive and a negative. And the subscripts here talk about the classes. So anchor positive are the same class, and then the negative some other class. And again, remember that triple loss sees the 3 elements as one training instance. It's actually all 3 together contribute to training. It's not just like we're training on one or the other. It's all 3. So that's one. And maybe that negative turned out to be a crappy negative. -2 for anchor positive 1 gave me a loss of 0. That's like, oh, that's sad. I did all this work of forward and backwards, and I got no loss. That sort of sucks. But remember, we're doing things batched. So say I had a batch of 2 elements, and I've got anchor positive negative and another anchor positive negative, and both of those turned out to be bad negatives for these anchor positives. That would sort of be annoying. But we've done all this work, and we've done all the forward pass, and we've done all this calculation of distances and stuff. What if somehow we could use all the negatives and compare them to all the anchor positive pairs? Because maybe this -4 is actually a good negative for this anchor positive 1. But the way we treat things generally with the batches is that we treat them independent. Like each row is just completely independently. So if we can work out a way to use the negatives in all the instances in a batch, we could make a great bunch of reuse. So one way of framing that is to say, let's not use negatives at all. Let's just have a batch of anchor positive pairs. And what I'm going to do is I'm going to fabricate by doing this sort of cross product and use all the positives as effectively negatives for all the other pairs. And so if I have n of these pairs, this is called n pairs loss. And this is great because you can imagine here, we get this exponential growth here, because this is a batch size of 3. What if I had a batch of 1,000? That'd be great. I've got basically 1,000 plus this huge number of effective negatives. So you get like a million, almost a million instances. And so this idea of using elements in a batch and using all the negatives as effective negatives for all the other pairs gives us this huge multiplication in effective negatives. So that's a big win, big win as the batch and batch gets bigger and bigger. So we got that's something again to stick in our toolbox. We did the triplet loss. It was sort of it has that problem of the negatives aren't always really great, but if it would be really great if we could be effective and use all the negatives in batch. So we're going to sort of remember that as something in the background. Okay. A little bit on geometry, just to tie a couple of things together before we.
Hey Matt, before you move on from there, can I ask a super simple question?
Yeah.
On if you go back to the n pairs slide.
That one.
When we have our negatives, do we just make sure that they are negatives? Because if we're mixing it in, it could like accidentally be a positive.
Yes, I'm glad you raised that, and I was going to brush over to the end. I was actually going to come back to this. So, are you okay if I actually come back to this point, which is really important?
Absolutely, man.
Yeah, and actually, what's really interesting, I'll give you a teaser at least, and it's not much of a teaser because the talk's not that long, but that this is this idea about what is an effective negative and what isn't allows us to move from supervised versions of this to completely unsupervised. So a lot of the more interesting results around this don't use label classes at all. But yes, in this case, there is a very big assumption that the classes are distinct in the way we framed it so far. And I was gonna admit to that in a little bit, but I'll admit to it now. And that actually can cause us grief as our batch sizes get bigger and bigger and bigger. So nowadays on modern hardware, especially some of the big wacky TPUs and stuff, batch size of 4,000, who gives it? Like it's great, whatever. So, but if you don't have 4,000 classes, it's like, sorry. So we've got this weird constraint now that if you had a small number of classes, as I framed it right now, we can't make use of it. But yeah, really good point. Luckily, it'll all disappear as we multiply some things away, but I'll come back to it, yeah. Okay, so a little bit on geometry, not too much, but let's take some vectors. Let's assume we've got 3. Let's think about 3 vectors that are a length of 1. So they're unit length. Unit length vectors are awesome. So one really important thing that we have probably all used many times is this idea called cosine similarity. So it's a super useful tool for us. And it comes from this formula that says that the cosine of the angle between 2 vectors is their dot product divided by the product of their magnitudes. And the great thing about unit length vectors is that their magnitude is 1, so that denominator disappears. And so the cosine similarity is equal to a dot product. And oh man, everyone loves dot products. Yeah, they're fast and they can be injected everywhere. So this idea of using vectors and putting these constraints on them to make them normalize this unit length is really handy because it means that we can do things like this. The cosine similarity is just a dot product. And dot products are really nice. There's a couple of reasons why dot products are really nice. They have this constrained values. They don't 1 to -1. It doesn't matter how big the because you've got unit length now, you've got this constraint of how big the dot product is. And they have this behavior generally that that cosine similarity, that dot product, will tend towards 1 as A and B get close in Euclidean sort of idea. As this B sort of moves around the circle over to A, the dot product will tend to 1. They're 0 if things are orthogonal, which is most of the case. As often we don't deal in 2D. We often deal in a higher dimension, and higher dimensions definitely everything's orthogonal. And then they go to -1 as they move apart. So yeah, and when I was first thinking about, I remember first thinking about this ages ago when I was first thinking about this idea of unit length vectors and thinking, oh, it's so restrictive though. Like if I'm in 2D and I'm only thinking about unit length vectors, all I'm thinking about is the circle. And that seems really dumb because what about the rest of the plane? But the whole point of this is as you go up through dimensions, you recapture that expressiveness because the surfaces of these hyperspheres are enormous. And if you ever feel like you haven't got enough, that's fine. Just add a couple of dimensions and you'll be fine. So this constraint is actually not much of a constraint in terms of expressiveness. And one thing that's important, because it's going to start to tie back to the other stuff we talked about, is that if you have 3 vectors, because I drew 2 here, but we talked about 3, didn't we? If A and B are closer than A and C, so if the distance between A and B, like in terms of Euclidean distance here, is less than A and C, and their unit length, then it means the dot products of A and B will be higher than A and C. And this is the equality we're talking about before triplet loss. We're talking about anchors and positives and anchors and negatives. If we have things at a unit length, we can sort of frame things like triplet loss, this idea of the relationship between anchors and positives, not in distances, but in dot products. And that's nice because dot products will go everywhere. And so concretely, this idea is we're going to use unit length embeddings when we talk about things, because we can then use dot products as measures of similarity without having to calculate distances. So that's handy. Okay, so there's a bunch of random sort of stuff that I've just talked about. I talked about probability distributions and like cross entropy. What's that got to do with like negatives in a batch? And now I've said something about who cares about dot products. It's like, let's tie all these together. They're foundational to this next part, which is how we use cross entropy for training these metric learning models, which seems a bit odd. So let's go through a flow. And this is actually it's in code. It's hardly code. It's pseudocode. Just put some brackets somewhere and suddenly everything's code, isn't it? But anyway, let's pretend we have this idea that we're going to be training. And the way we're going to train this thing is that we're going to sample some images across some classes. So again, this is what Andy referred to before. There's this assumption implied in here a little bit where each of the instances that are in this sample are distinct. I'm going to call them anchors. Do the same thing again. Sampling, and I'm going to call the positives. And with this constraint that the nth element, the ith element in each of these is the same class. So these might be my anchors, the circle, triangle, square, and these are my corresponding positives, circle, triangle, square. And the idea is again that each of them is random. Each of the anchors and positives is the same along the indexes, but each of the anchor positives, each anchor and each positive is different. So these are circles, these are triangles, these are squares, and the sort of row wise that are always different. That's the thing we're going to do as part of this sort of anchor positive sampling. Now that I've got those images, I'm going to run them through my model. So I'm going to run the embeddings. This is an embedding model. We're training this metric learning embedding model that takes something, in this case images, and outputs embeddings. And at the side here, I've got a bit of this pseudo shape. So when I embed the anchors and the positives, I get this matrix back, which is n by e. So n is the number of instances, in this case it was 3, and e is the embedding space size, 16, 128, whatever. And when I embed these sets, then I get this, because I'm doing this batch, aren't I? I'm batching, I'm getting all n of them will have an embedding of e. Cool, so now I've run my anchors and my positives. I'm going to do this calculation, which seems a bit arbitrary, but we'll come back to why I've done it. I'm going to take the anchors and I'm going to matrix multiply them by the transpose of the positives. So what am I doing here? I'm taking these anchors, the n by e matrix. I'm transposing the positives. So I've got an e by n matrix, and then I'm matrix multiplying them. So n by e times e by n gives me n by n. And I called it sims. And why did I call it sims? It's because if you think about what a matrix multiply is, it's a row by column dot products. So if I think about this embedding matrix down here, sorry, this what I've called sims, because it's like similarities now. Because it's n by n, because I had n anchors and n positives, and I've got this interpretation, which is exactly what matrix multiply is, that the ijth element in this matrix is the dot product of the anchor and the positive, the ith anchor and the jth positive. So if I look down here, so I've just sort of drawn them on there. These are my anchors and these are my positives. And this talks about all the pairs of what I do here. It's a bit like a grammar matrix. If this was anchor by anchor transpose, it's like basically all the pairs of dot products. And so just imagine this is what my sims look like. Just say my model behaved that it gave me this sims matrix. If you look at this first one, the 0.9, positive 0.9, and then these values, the other values are low. And if I go to the next row, so that sort of says the circles, if I think about this unit length embeddings, that's a high value, and dot products high mean that the points are close. So the circles are close because they got a high dot product. If it was 1, they're the same thing, yeah. But the other values are low. So the circle is far from the other two. That would be a good embedding for those circles at least. But because we're doing these pairwise, we get to look at all the other ones too. So if I look at this next row, the triangle versus triangle is 0.8, and the triangle versus the other ones is low. So the two triangles are next to each other, and they're also far from everyone else. Because remember, the high dot product meant close, and low dot product means far away. And the same with the squares. So the squares versus each other are high, and the others are low. So the circles are next to each other, the triangles are next to each other, the squares are next to each other, and they're all away from each other. And, you know, all the squares and circles and triangles from each other are far away. So that would be a good embedding space for these images. So this is the sort of thing we're looking for. We're looking for this sort of idea. And I'll pack that up a little bit just so we've got a bit of space. So if this was my anchor and positives, and under that constraint we talked about that each one was the same and they were all distinct. If this was the Sims matrix I got out of it, I would say, good work, model. Don't, you know, that's a low loss case. And if we look at this and tie it all the way back to what we saw, oh my God, I could just call these Sims logits. And what were the logits trying to do when I gave it to the cross entropy, the sparse softmax cross entropy? It said, try to take the labels, the indexes you give me, make them high, and make all the other ones low. So if I take this Sims matrix as it is now, jam them into this function, which was generally originally made for independent probability distributions, along this sort of scheme. If I'm dealing with these dot product ones, the label now is just basically the sequence. It's just basically range 3, because I'm saying they go together, they go together, they go together, and I can actually just bolt that in range 3. So this is the crux of my talk. The fact that we've got this under the hood piece of tooling, which is available to us, that is well understood and just available as a library function that was made for independent probability distributions. But if we want to use it for metric learning, we just have to go through this sort of bizarre combination of things, including the Sims matrix, and then we just pass it directly to this function as logits. We just call them logits, and it just works. And so there's this. I love these sort of things where they just work, because they talk about a really deep relationship between things, really deep, because there's something deeper than just logits here under the hood. And so when I first saw this, I just went, angels sung in my brain as I tried to connect the two dots of these things that I thought were unrelated, but they're actually very deeply related. So I think those sort of things are always really fun to see. Cool. So now that when I got that and I saw it, I started seeing it everywhere. And so recently, you know, and you know what archives like, you search for papers in an area and you find lots of papers in that area, and it's like nothing else exists. So for the last couple of months, all I've been looking at is metric learning, and it seems that according to my searches, that's all that everyone else has been doing too. But so one thing that I want to talk about though is this little bit before I just brain dump some papers, which touches again on the idea of what the anchor and positive meant. This is one last little closing thought. And this idea of the anchor positive and negative being sampled by classes is the fundamental supervised approach to this sort of stuff. But what's really interesting, and this is, you know, used in a lot of state-of-the-art models now around, there's more and more, this supervised learning is dead, and it's like long-lived, you know, pre-trained in an unsupervised way if you can get away with it. So one thing that's interesting recently is this whole idea now that if I had this idea of anchors and positives, one way of generating anchors and positives is with augmentation. So what I'm going to do is I'm going to take an image, some random image, it doesn't matter what it is, and I'm going to generate my anchor and positive by running augmentation across that image. And you know, the idea of augmentation is that you spin the wheel and you get a different image every time, don't you? And you know, whether it's images or whatever augmentation scheme you have, what's the goal of augmentation? Why do we do it? It's because we know that there are invariants in images. Rotation is a great example, isn't it? Rotate by a little bit, that fundamentally shift the image in pixel space, but shouldn't break the class label. So if I take a picture of a cat and I rotate it by 5 pixels, all the pixels are different. Well, they're not all the same, but you know, color blending, whatever, but most of the pixels have shifted, but it won't suddenly change the cat to a banana. So we use augmentation all the time for generating more data, for making the models more robust. And that idea of saying they're the same class can be used here too. So this idea of metric learning can be totally used without labels. You don't need to have labels at all. So all the things that we've talked about so far can be sort of rewritten in a sense by using this idea that I'm not going to actually use labels at all. My positives will be just differently augmented versions of my anchor. And then the negative just becomes, again, any other positive. So, which is, effectively an augmented version of any other image. So this is great because, and this is one of the big, I'm seeing a lot of work around this, because anywhere where you can use a system that doesn't need labels is going to win. It's going to win because labels are costly, and we get more data than we get more labels. So if you can make a big breakthrough, even if it's a lot of these things are about, in a sense, this is like a pre-training step. A lot of meta learning deals with this idea of trying to build a model that's based on an embedding model. For like, this is something I've used in a client project. This pre-training with these type of embedding models to very, very rapidly then do few-shot learning, because the embedding space is awesome, and you're doing the explicit classification job you might want on that embedding space only requires a little bit of samples, because you're in such a nice, beautiful space that you can get away with like single-shot learning. So it's a big one, I think. Yeah, so lots of papers, and I'll share this at the end. So a bit of a paper dump. One thing that I thought was really interesting is this paper I found just the other day, which is like a much more formal version of this talk, basically. So it's pretty embarrassing. But anyway, it was interesting to read. But yeah, this last one as well is interesting. It's, again, that idea of using this pre-training step of basically using this unsupervised idea of augment the anchor and positive to pre-train and build this embedding model that is then tuned, basically fine-tuned to ImageNet. That's one of the state-of-the-arts on ImageNet at the moment. But state-of-the-art on ImageNet, it would have changed 3 times during this talk, so who knows. Okay, where I'm using it, I've been using this a little bit on this. I've had this pet project for ages. I'm trying to train an embedding-based YOLO, completely unsupervised. So just get it to sort of look at images and work out stuff. And so everything we talked about here with the embedding matrix, one thing I love about convolutional networks is this deep relationship between a 1x1 kernel convolution and a dense layer, means that you can rewrite anything like an embedding layer as a 1x1 kernel, which means that these things automatically become fully convolutional. So I do this training on these random sort of crops, but the application of the model can be run fully convolutionally, which is important because get the scaling variance and stuff. A couple of things that I thought were interesting about this is I can't use that sparse logits. This is something, again, touches on that point that Andy made. The idea of saying that the one way of getting around the problem of having multiple instances of the same class in a batch, you can solve that by not using the sparse representation and just normalizing what your true looks like. So if you have 2 things that are meant to be the same, then instead of 0, 0, 1, 0, 0, you just 0, 0, 0.5, 0, 0, 0.5. So you can sort of talk about, you can assign the true distribution to be representative of the fact that if you do have more than one positive in your sort of batch thing, you can sort of just roll it out like that, and the loss works. What I thought was really weird is that I did all this stuff, and it was really well working with everything being unit length. And then when I got to actually doing hyperparameter tuning, as a good engineer, I assumed nothing and put everything under the control of the hyperparameter tuner, including whether I normalize things. And I got this weird result, and it's just consistently the case where my test results are better when I use normalized embeddings. But during training, I don't use a normalization. I actually allow the dot products to be outside of that range. And I think maybe this is something I'd love to write up the numbers sometime, or actually go through it on a whiteboard. I think it's to do with the idea that when you've got these unit length vectors, if you do allow them to be different lengths, you're providing so much more expressiveness in the way that the learning will work. So even if there is some motivation to put them on the unit sphere, sometimes treating that constraint is actually better represented through things like regularization. So I'll allow you to do whatever you like, but I'll penalize you from your distance from the unit sphere. And that's what some people end up doing because it makes training more stable. But again, why it makes training more stable, I'm honestly not 100% sure. But yeah, but it's an empirical result, deep learning and empirical results, who would have thought? Another thing that I think is really interesting about this project, and that I love, is that idea that when you talk about who's equivalent in the unsupervised case, you can do a lot of work with just basically random embedding matrices. So these are always fun. Just take this huge amount of data, run them through random embedding matrices, so not actually trained. And the thing about them is when you have a whole bunch of them, you can just basically look at near neighbors in that random embedding space. And because even without training the networks, more often than not, and this is the classic thing with signal, isn't it? You just need to be more often than not. Two things that are of the same class will probably be embedded close to each other in the random embedding matrices. And as long as it does that more than not, you can just use random embedding matrices for labeling. So the way I've been training this is without giving anything to do with labels. So this thing, just to go through this example, because I just cut and paste it. I've got an image here. This is a test image, a little blue square thing. And here's a source image that it's comparing against. So it's basically saying, do this comparison against this little crop, against this entire image. And then I get this basically heat map. And black is points where it thinks it's very similar. And gray is white is where it thinks it's unsimilar. So you can see this little blue one here, even though it's different, it's sort of, and I mean, in this case, I think maybe it's sort of cheating a little bit here because of color. It's pretty easy to pick color. But I picked a bad example because it does actually work more than just color. It works on spatial aspects too. But it's saying that it's more, this image is more, has a higher affinity with this part of the image. That's a little bit there. And so, yeah, and this one too, you can see this weird T thing is more aligned with this T thing. And this interesting one down the bottom, this idea that I've got this little blue thing that doesn't actually appear in this image. This was a completely held out one. And if I look at the affinity of this, it's the white is not the same. So it's very sure it's not those objects, but it's unsure about the background. The reason for that is because the background's the same, even though the foreground object is different. Anyway, this is just a little project I've got working, well, that I'm working on. It certainly doesn't work, but I'll make it work eventually. Okay, and the last thing to remember from these things, remember Sammy Jenkins. And I hope that at least one person gets that reference from one of my favorite old films. That is it. That is the end of my talk. Thank you so much for listening. Is there any questions?
Thank you. Actually, I had a question in terms of training using the cross entropy loss. So as you mentioned, like since we are not normalizing a feature vector or that comes in the final FC layer, when we train using the distance like a triplet loss or something, so if the 2 points are nearer in some aspects, whereas when you normalize and try to compare using cosine distance, so in the embedding space, like if the feature vectors are farther, when you normalize it, it might come together in a unit sphere where the angle between the two is very less when you compare between the positive and the negative class, whereas two positive class can have a bigger angle, right?
Yeah.
So how do you, something without normalize, like while we train without normalizing it, but we compare normalizing it and trying to compare using cosine loss. Do you have any insight on that?
Yeah, so one of the things interesting about the cosine similarity, if I go all the way back to here, I'm still sharing, aren't I? Yeah. The cosine similarity is this idea of this, that it has this clipping type behavior when they're unit length, that the dot products are constrained between 1 and -1. If we don't have that constraint, I'll see if I got your question right or observation right. If we don't have this unit length constraint, then the dot product is unbounded. It's not no longer clipped by 1 - 1. And that's actually okay because we're using that logit form of things. If you go all the way back to the Softmax cross entropy with logits, even though the probabilities have that constraint after that normalization, there's no such constraint on the logits. So the way this is formulated, this Softmax cross entropy with logits, it's fine for these values to be unbounded. They can go from negative infinity to infinity, and it still works. Okay. So if those vectors aren't, if the anchor and positive are embedded in such a way that, well, in fact, well, there's one thing I will touch about on this, and it's something I skipped over in the slide for time, but I'll talk about it now. So if we don't normalize them and we get these dot products that basically can extend out to infinity because there's no constraint on the embeddings, we will get pain there. And so this is often why we want some form of regularization. There is an interesting aspect though of the fact that because we're training this one sort of anchor positive pair against all the negatives at once, there is a really nice form of regularization that's happening here, where there's as much negative pressure to pull it back towards, or away from the other ones, as go gun-ho with the anchor positive. So I think that's part of it. Another thing that's really important for stability of training, and I guess, it's always the devil's in the details, isn't it? There's this interesting thing that's really important to do, which is called temperature scaling. So if you think about those logits, so these are the values before the normalization. what's often really important to do is we have another actual hyperparameter there, which is called temperature. And the idea of the temperature, this comes from this is the same thing you would have seen in Softmax maybe about sampling. This idea that we're going to scale the logits by some amount to make the distribution more or less uniform. So what we'll sometimes do actually, this is another hyperparameter we do, and maybe it's also a hyperparameter we anneal it away, but we start with something that forces things to be more uniform, to make things stable at the start, and sort of goes away later. And we do that with this idea of a temperature. And the temperature is basically just dividing the logits all by some value to make them. Because you think, again, that normalization idea means that if you were to divide all the logit values or multiply them all by some value, it would make the softmax values more spiky, or it would make them more uniform. So that's another thing we end up doing. But yeah, thanks for your question.
Yeah. So just one more quick question I had, like in terms of like since we have many methods to do this metric learning, so one of the question I had is like, if you try two methods, what is your usual metric to say that okay, the representation which I learned is better than method 1 to method 2? How do you usually do that? Do you have any?
Well, held out, the loss value has a clear interpretation, and held out loss is what I usually use. So I've got some held out data with ground truth, and I can actually just run that loss function through, and it gives me like a function which is very interpretable as loss. So maybe is that not what you're thinking?
Actually, one of
like
the metric I mean people use is that the normalized mutual information is something which people use. That is something which gives a single metric saying that how well the clusters are together. I mean, the positive samples are well together when compared to the negative ones. So even though I have not used much, like I was interested to see what do you use and how do you.
Yeah, and I mean, to be honest, the big thing with me, and I think about evaluation, especially when you're actually using a system, when you're actually using it for something, there's things like loss, which is training, but really no machine learning model is used entirely in isolation. It's not like the output of a machine learning model is what your business is. Your business is using that machine learning model for doing something else. And so I'm quite bullish on always saying evaluation is on that thing you actually care about, because things like loss are a proxy for how well your model does according to some training set. But that's no guarantee that the model is in any way useful or good for the end goal. So the evaluation often, you're right in some sense that so for something like new neighbors, there's something where these new neighbors are being used in some system. And really, you know, I've had this in the past where I've made an improvement to a system and we've all gone high five team and high fived each other. And then a downstream system of us that actually made money said, what have you done? We were somehow dependent on your crappy behavior that you told us was crappy. Roll back. And so we have to, of course, roll back, because what does our evaluation matter? Because we're not actually touching the users. So I think it's quite important to understand that evaluation.
Yeah, I agree. Yeah, I mean, depending on our end use case, the metric which we use should be tuned to that rather than depending on something standard.
Yeah, good points. Thanks.
Thank you.
Hey Matt, can you hear me all right?
I can. Hello.
Yeah, so I feel like I'm going to be a stupid questions guy. Here's a stupid question for you. I know one of the things that's nice about using this kind of like Softmax in general is the Softmax on the logits around certain areas is like somewhat, you get like a somewhat constant error signal. So like if you were to just, in the Sims matrix, like where, like on the diagonal, just backprop, like have the error signal as 1 and off diagonal as -1 and just backprop that. Do you get a similar training effect?
Yeah, because the zeroing of the Y true, that's actually what ends up happening. But if you think about that all the way back to that cross entropy, that summation of Y true times Y predicted, log Y predicted, means that it didn't matter in terms of the loss and the backprop, because the backprop will see that 0 and throw that away. So that's exactly what ends up happening. That in fact, that's a really good point. So is it completely, are you saying it's redundant to do the full matrix multiply and actually just do the...
No. I'm not saying
I have to do it. Yeah.
No, you have to do the matrix multiply. I'm just saying that I think yeah, you would maybe get a similar effect if you literally just back propped like 1 and -1 straight into.
Oh, I see what you're saying. Yeah.
Because basically you're saying just make this look more like a identity matrix. Yeah.
Yeah, I'm going to give that a go. I wonder if that's yeah. So there's an interesting thing, and I've been trying to look at this in terms of the there's this it's something again I don't, and yeah, you always come up with these like it's going to be a stupid question, but it's actually really deep and complicated. But the idea I think of I'm always trying to grapple in my head and get better sense of like what is the difference in behavior between a single instance being trained and the entire data set being trained versus the sort of variance sort of thing we get from batching. And so the way we normally run these is on very large batches, like because we can make like 1,000 at a time, and the convergence rate compared to the triple loss is astounding. It's so fast, it's so fast. If I can just compact them in, and I think that there's an element where there's this huge value of that because I'm just comparing to lots and lots of negatives. And so when I look at something like making the batch size bigger, it's a much bigger impact than something like temperature, tuning the temperature, because the temperature is changing the per element, whereas the batch size is just looking at way more at a time. And so I think what you've commented on is like an extreme version of this. If my temperature, because I could do this with my current system just by picking what do I want? I want a really large or a really low temperature. But anyway, or I could just literally, or like you said, literally just jam the identity matrix in there and see what it does. But yeah, because the bigger my batch is, the main point is that I'm comparing more things to other things. Maybe not the actual magnitudes of the comparisons. Does this -3 versus -4 actually make a difference in this mammoth matrix? Maybe not. Yeah, really, really interesting point.
Yeah. I think there was this other paper. I'm not sure if we discussed it. I think I mentioned in the news, but I think overall there's a lot of interesting. Their claim to fame was this state-of-the-art performance. Like downstream, basically we're saying, okay, you can pre-train with ImageNet or you can just pre-train unsupervised with their system and you'll get the same performance. That was their big claim to fame. And that was all, use augmentations to say things that are like different crops of the same picture should be similar. And that seemed to be the magic formula. So, and I think that like some people call that whole area like self-supervision. Yes, and I know that's been like a popular topic around because I think it's kind of like you get some of the benefits in terms of stability of supervised learning, but then you don't actually have to have labels, which is nice.
I think I'm fascinated with the contrastive, the self-supervised stuff around contrastive. Actually, the first time I implemented triple loss was helping someone out on this thing, and I reproduced the result later on this thing called time contrastive networks, where you take 2 images of a scene, a robotic grasping, and you basically say, I'm going to take 2 videos of looking at things, and the anchors are going to be examples. Yeah, the anchor and positive are going to be 2 view frames so I'm going to take at a time t, same time, my anchor is 1 viewpoint, and the positive is the same scene at the same time from another viewpoint. So I get totally different pixels, but they should represent the same thing semantically because they're different viewpoints. So that's my anchor and positive. And my negative is another point in time from the anchor's video stream in like 10 seconds or something. And that's really hard because the negative looks very similar pixel-wise to the anchor, and the positive looks very different. And what's interesting about it is that there's lots of ways you can anneal this. You can put the cameras next to each other. That makes the anchor and positives easy versus making them harder and harder. And you can pick how far away that negative is. If the negative is really far away, like an hour in the future, it's likely to look very different. But if it's like the next frame, it's like, God help you, because it's almost the same pixels. So that idea of contrastive learning, using a signal which isn't the main label, that gives you this hint towards a label. This idea of that's a form of labeling function. And I think they're fascinating, these sort of things, the self-supervised.
Yeah, absolutely. And I had one like mind-boggling thing, which is I remember seeing a piece of work which was basically using fMRI to look at patterns of activity in the hippocampus. And you have this situation where if you show people like images, like totally different images, but say of the same park, the fMRI, like the similarity between the activity in their hippocampus will be similar as well. It's kind of like the fMRI activity in the hippocampus is like kind of analogous. Like you can actually use it as an embedding of like images, which is mind-boggling.
Wow, that's pretty cool. But probably totally different across people. There's like this, you've got an embedding space, I've got an embedding space, and maybe we need to just project it and rotate it. And this is how we're going to share thoughts. We just got to work out what the projection is between our two sets of thoughts, and then I'll just inject my electrical signals into your brain, and we share memories. So yeah.
So, sounds good. We're working on that tech at the moment, Matt.
What could go wrong? What could go wrong? Any other thoughts, mistakes?
I guess speaking of sharing embedding spaces, maybe not across brains, but have you been thinking or tinkering with different kinds of embedding spaces for your actual model? We talked a lot about like the metrics you use to evaluate those sorts of things, and less about kind of what manifold you were trying to embed things on. Is that important for the kinds of projects that you've been working on?
Yeah, mostly the hyperspheres are really nice, again, because of that dot product idea. You just can't go past having the idea of similarity being expressed in dot products, because then you suddenly have everything available to you downstream. And so one of the first times I used metric learning was in search. Basically re-ranking. So, you know, when you do search, there's this sort of relevance recall types, you know, pipeline of things. And one of the things that often happens is a bit of a, what they call twiddling, where you sort of decide, are you going to flip some results? And a lot of search engines provide that idea by saying, I'm going to allow you to express similarity between things based on dot products, because dot products are such a fundamental thing. So time and time again, I find that I'm motivated to express things that capture that idea with a dot product, because then I'm allowed to use it in some sort of system, and then that forces me to basically work with circles and spheres and stuff. But I think there's a bunch of really interesting ones. Like there's a lot of hierarchical interesting embeddings. There's like this Fibonacci style of doing embeddings. One thing that has caused me grief a little bit that I've had to deal with the idea of, and it goes all the way back to that idea of my original idea being, oh, we don't care where they go, we just care about a relationship. That's fine until you need to retrain the model. And then you're in trouble, because if suddenly you don't care about things, then every time you retrain or try to use some more data, you completely invalidate every other embedding you had. That's just a huge pain. So there is some things that you might want to do around trying to make sure that you can project from the old space into the new space with, like, you know, just can you learn a rotation that puts you from past into present, or constraints that people put around, particularly there's an idea called harmonic embeddings, where during this training you actually can, as a form of multitask, be learning your embedding space, but at the same time always sort of doing this comparison to your last set of embeddings. So you do this sort of combination of tasks, which is you're allowed to put it wherever you like, but you got to put it where you put it last time, basically, and sort of put them together. That's the only sort of other variant of
batch to batch, or
from last training run. So I previously trained model. Maybe you're retraining every week, for example, when you're getting new data coming in. You can't have a model that just completely invalidates everything from last week. It would just too destructive. But if you can sort of have this model off to the side that's acting as a form of constant, you know, either you start on that model and you tune, or you've got this other model that sort of allows the freeness in terms of the original optimization to happen, but always tries to steer it towards things that aren't too different from last time. Yeah, are you aware of some? Is that something you're interested in?
No, I haven't played with that sort of idea at all, kind of like training, but also keeping consistent with the previous model. So that sounds like really interesting to me. And I'm just sort of thinking about if there are good papers that I might want to dive into, because yeah, I haven't done anything with that at all yet.
The simplest thing I can think of is the first reference I can think of is in the original FaceNet paper, which talks about triplet embeddings, has a reasonably good section on harmonic embeddings. If I remember that right, it's been a while, but I remember the first time I saw it, and then from that you can see a bunch of references. It's quite well laid out, I thought, in that paper.
Cool.
Hello, can I ask a question?
Hey, how are you going?
Hey. Can you hear me well?
I can.
Okay. So I have actually two questions. One is like when we're using, for example, like cross entropy based losses, not just n pairs, but like the other variants as well. How important is that we use the entire like negative examples in a batch. So like this is going to be one question. Like I understand that n pairs like gives this opportunity for us, but like how important is it? And the other question is like when we compare the n pair loss and the triplet loss, let's say, we can get kind of like similar performances if we tune things pretty well, if we tune hyperparameters, etc. pretty well. So what do we lose by using n pair? Like what's the trade-off there?
Yeah, that last one I'm not sure about, but going back to the first one at least, yeah, that idea that if I think about the fully that huge matrix with all the values, like the dense version of it, there's lots of cases where, and this is a thing to do with classic negative sampling in some sense. We don't need to have the full distribution. So this is if you go all the way back to info NCE and stuff with the original training, you don't need to sample the whole lot. You just need to sample some number of them. So it's reasonable to have a trade-off between. I'm interested in the one that's meant to be the anchor positive. Maybe I don't care about every single other negative pair. I might just have some selective number of them. And that was the original sort of set of tools that was used for very, very large softmaxes. So the idea of the hierarchical softmax and stuff introduced all these ideas. So I think there will be a place where I didn't talk about it at all here. The idea about when you're using a hierarchical softmax, then the way you frame cross entropy is a little bit different. So I think that you could do that. It makes sense. I've never really thought about it too much, but if you had something like that, an equivalent, where you wanted to do something like the equivalent of hierarchical softmax, then there'd be an equivalent all the way down to what we talked about here. That makes sense. So that was the first part. And the second part, what do you lose? Yeah, it's a good question. I'm not sure. That's a good one. Can you think of anything?
What I thought was like, I mean, like when we use triplet loss, for example, like we can directly, like we try to directly manipulate the distances between these embeddings. But when we think of these distances or similarities in terms of a probability distribution, then like maybe we like lose some, I don't know, like magnitudes of these, like how important that these things are, like let's say 2 units apart, or you know, like when you convert to probability distribution, then maybe that's not that important that they are that apart, etc. I don't know.
No, I can see what you're saying, and I think it coming at it from the other way. One of my main motivations I had from going to triplet loss to these ones is that idea of stability, because when you're doing an instance at a time, you know, and again, it comes back to that fundamental idea of the positive and the negative. You're sort of just bouncing stuff all over the place. Like every example is changing this relationship between the triple, but forgetting about the fact that it's probably breaking it for other negatives. So that was one thing I really noticed with when I first started doing this training, that as I make this batch larger and larger, the training is slower in the sense that the movement is slower, but it's much more stable. The variance in things seems to drop heaps. And anytime I've seen where I can have updates being slower, but the variance being lower is fine, because the momentum-based optimizers just sort of ride through it, and they just speed themselves up as required. And variance, as long as variance continues to be low, that they just speed up in the right direction. But yeah, there's an interesting point in between that maybe if you have too many negatives, you are penalizing the idea about how anchors and positives together, especially maybe if you know, there's something here, again, just thinking aloud about how expressive the embedding space is as well. Because, you know, if you've got this hugely spec'd embedding space, you sort of learn these boring embeddings, so to speak. It's really easy to put things apart. Like the extreme version of this is you have like a 3-dimensional embedding and 3 things you're trying to embed. You just put them like on the axis, basically. It's not terribly generalized. So maybe this is well to do with, there's some trade-off here that's happening also to do with how spec'd your embedding space is. But maybe when it's under or over spec'd, one of these behaves differently. I don't know. I'm just thinking aloud, but yeah, it's an interesting point. It always feels like, one thing I want to say, it always feels like a hack. Every time I do one of these things and they sort of work, I just think, man, that's an accident that it worked.
Yeah. So Matt, I just had a brainwave while you two were talking, and it's very related, which is that there are these kind of deep connections between word embeddings and matrix factorizations, basically, and that was like really interesting work, because I think the inspiration for word embeddings have been totally neural, but then you had these results basically showing that, yeah, you know, you can look at it as like a low rank factorization of this like word context matrix. And it just came to mind that the Sims matrix, you could imagine if you weren't doing mini batch sampling, there would just be one giant Sims matrix, which is the similarity of every image to every other image according to your model. And the fully unsupervised version is basically just asking that Sims be low rank. You're basically saying that, like, I believe there's underlying structure, so therefore Sims shouldn't be full rank, it should be low rank. And in fact, this seems to be a way of kind of moving towards that using the tools we have, kind of massaging it into being lower rank. So it does occur to me that that's the connection between sort of like cross entropy for metric learning and matrix factorization. And that also then draws the analogy to things like when you do skipgrams, for example, like basically you could imagine an embedding skipgram model where you take like 3 crops of an image and you like either swap one out or not. And you ask like, yes or no, did this crop come from the same image? If you know what I mean.
Absolutely, yeah. Absolutely.
Yeah, and that would be kind of like literally the CNN skipgram.
Yeah, and there's something that I think one of the chaps just talked about as well, that mutual information. They're all the same, they're just from different angles, aren't they? So yeah, I think one thing I like about when I see this, and like in hindsight, it's just like, oh, that's really obvious. But now I'm just looking for the other combinations of things that, oh, that's really obvious. And yeah, I think there's 2 dimensions of it. This idea of this deep duality between all these things. There's this, they're the same as this, is the same as this, the same as this, is the same as this. They just use whatever one makes sense. But there's this other axis which you just touched on, which I think is fascinating, is about what does it mean to be an anchor versus a negative. And like when you look at a recent paper of this, it is very, very empirical based. The main contribution of the paper is like, we tried all these huge combinations of things, like a crop in a crop, or a crop next to a crop, or a crop without overlap or whatever. And just these empirical results on one does better than the other. And so it feels like there's this 2 axes of like deep theory that's the same. And then there's just like free-for-all hacks around what does it mean to be an anchor versus a positive, and whatever works just works, and we'll use that for our problem. So yeah, it's fascinating.
Absolutely, Matt. I would actually say a lot of modern deep learning at the moment is trying to come up with like smart, efficient ways to encode inductive biases. So I mean, like, it's kind of oblique, but obviously like in a CNN is a clear inductive bias. And I think we've discussed this before at the Meetup as well, which is like knowing that if you augment this image, I have this function, and knowing that if I apply this function to an image, it preserves the class, is actually a huge piece of information.
Yeah.
You just have to kind of like extract the value out of it. So in a lot of ways, what we're finding is like just better ways to tweak this, like ways to put our intuitive inductive biases into these models.
Yeah. And then you start down the whole road of the adversarial side, looking at it the other direction, where like you've got things that look the same, but somehow force the network to completely change its behavior. So all these sort of things, I always look now with the eyes as well of like, hang on a minute, what's the reverse version of this that someone's going to use to attack me? So fascinating stuff. Are we done? All good for questions? That was great discussion, everyone. Thank you so much. I'd learned something.
A little like this. There we go.
Yeah, there you go.
I'm clapping at home.